My name is Clark Zinzow. I'm a software engineer at Descartes Labs, and today I'm going to be giving a talk on a Dask and Ray integration that I contributed to upstream Ray. And the company that I work for at Descartes Labs has been using this internally to offer a massively scalable geospatial data analytics product that allows remote sensing scientists, data scientists to analyze petabytes of remote sensing imagery and vector data and scaling up their computations to tens of thousands of cores. Lots of fun. Brief overview of the talk. I'm going to give an overview of the Dask ecosystem and the Dask Distributed, which is a particular task execution framework and scheduler for Dask. I'm going to go into some of the pitfalls of the Dask Distributed systems architecture, especially for the production data analytics use case. I'm going to give an overview of Ray's programming model and briefly talk about Ray's architecture. I'm going to describe the Dask-on Ray integration, and I'm going to demo and talk about the massively scalable geospatial analysis product workflows that Descartes Labs has been developing, and how exactly it uses Dask and Ray. So first, what is Dask? For those that don't know, Dask is a parallel computing library for Python, very much so geared towards scalable data analytics. And Dask integrates very nicely with like the Python data science ecosystem by providing these ndarray and dataframe abstractions that extend the very familiar interfaces of NumPy and Pandas. That if you've ever done Python data science or Python, machine learning, if you ever did research as a scientist, I'm sure you're very familiar with those interfaces. But unfortunately, those interfaces are to a library that's generally built for in-core single machine workloads, and Dask provides those same interfaces, but under the hood, it will partition data and it will farm underlying tasks on that partition data out to multiple cores or out to multiple machines, enabling larger than memory workloads and enabling you to run your ndarray or dataframe data analysis on a distributed environment on a cluster. Brief overview of the Dask collections and the broader ecosystem. Dask arrays mimic the very familiar NumPy API. The Dask data frames abstraction mimics the Pandas API, the Pandas data frame API. Dask ML implements the scikit-learn API, and that allows you to do very basic model training and inference on Dask. And then Dask bags mimic the familiar PySpark APIs, and then if you're familiar with iterators or the Python-specific tools library, Dask bags offer a very familiar API to those, very similar API. Dask has three big core components, the nice stratified layers that we can talk about. There are the collections abstractions. These mimic the interfaces of those popular data science libraries that I just mentioned. There is also the Dask delayed concept, which allows you to wrap custom arbitrary functions. So that gives a ton of flexibility. There's the task graph specification, and that's for representing the imperative operations on those collection abstractions as a DAG of function application tasks under the hood. You can think of that task graph either as like a bunch of tasks that are just simple Python function applications, and you can also think of it as like a data flow graph of data flowing through operator nodes in the graph. And then there is, of course, schedulers and execution backends for executing that actually executing that task graph. And that allows you to execute a standardized graph spec either on a single core, multiple cores, or even multiple machines across a cluster of machines. The Dask task graph specification is pretty simple. First of all, the task graph, it just captures data dependencies of graphs. Each node in the graph represents an operation, which is it's just a Python function. And then each edge represents a data dependency between two operations. And it's just represented in memory as a simple Python dictionary. As for actually scheduling and executing these tasks, Dask will schedule these tasks for execution on one or more cores, or on one or more machines. They provide several scheduler options out of the box. There is primarily a delineation between the very simple local schedulers that will execute on a single node. And there are three big ones. There's the synchronous scheduler that executes tasks serially. There's the multi-threaded scheduler that will execute tasks over a thread pool. And then there's the multiprocessing scheduler that will execute tasks on a pool of processes. Most uses of the local scheduler will use a multi-threaded scheduler, but the multiprocessing scheduler could be good for tasks that will not release the GIL. But most things that do like either do like I/O or that call into libraries like NumPy and Pandas that will release the GIL as soon as it leaves Python land and goes into Python and C land. And then there are two forms of the distributed scheduler. There's the local version, can be run locally, which is advantageous because it's pretty smart. And then there's it can be run on a cluster where there is a single global distributed scheduler, or there's a single global scheduler that is then able to distribute work to multiple nodes, and it's for executing tasks on a cluster of machines. And as soon as you really need to go to distributed execution, the distributed scheduler must be used. That's the primary and really only option in the Dask ecosystem right now. Now, there are a couple of pitfalls of Dask Distributed, particularly for the production data analytics use case. That global scheduler is both a performance bottleneck and a single point of failure, which is not nice. There's no scheduler fault tolerance yet. There's no follower leader pattern. If the global scheduler goes down, you'll lose all like in progress tasks, and you'll essentially have to like restart the cluster. Maintenance and introspection of like the cluster and task state adds to the task scheduling overhead, which is not great. So if you're looking at the dashboard, that can decrease the scheduling throughput. The scheduler is written in Python, and so naturally it inherits a lot of Python's performance characteristics and resource footprint, aka it can be bad and suffer from bloated memory utilization, for example. It can't be natively or naively scaled. You'd have to resort to sharding schedulers, which for right now will be equivalent to sharding entire Dask clusters. So if you have a cold shard, for example, well, one, that's a lot of architectural complexity, a lot of infrastructural complexity to add. And then if you have a cold shard, you then might have a lot of wasted worker resources, where a lot of like a cluster of workers will just be sitting there because they are not getting hit very often in the sharding pattern. The clients are generally designed for end users, not really for like a large production system. It's assumed that clients are long-lived. It's assumed that there's going to be frequent communication. And the API is generally kind of meant for like, you're using it from like a Jupyter notebook or something, instead of calling into like the Dask cluster from like a highly available, very scalable service that lots of clients calling in. It wasn't really designed for that use case. And there's only very nascent support for stateful execution, which becomes an issue when you start moving to stuff like fault-tolerant machine learning training, as one example. Anything that you want to do that's stateful. So yeah, given these issues, how could we potentially execute Dask graphs on a cluster of machines without using Dask Distributed? And so, of course, we're at Ray Summit. How about Ray? Could we potentially use Ray? Quick intro. It's a framework for building distributed applications. And under the hood, it contains a really cool, really fast next-gen task execution engine, emphasizing performance and reliability. You can see the Ray devs talk about that a little bit more in the Ray 1.0 white paper that they put out. But they're really focusing on ensuring correctness in the face of failures without compromising the happy path, without compromising the performance characteristics, throughput, latency of the very common case where nothing fails. And that's very hard to do. But the resulting product, after all the engineering effort, you get a fault-tolerant uh, task execution framework that's capable of extremely high task throughput. And then the key architecture paradigms, particularly highlighting the differences between Ray and Dask Distributed. It has a decentralized peer-to-peer distributed scheduler, so there's no global scheduler bottleneck, which is really nice. All cluster and task state still has to be centralized somewhere, and in this case, it's centralized in the global control store, which right now is backed by Redis. But it makes all those decentralized schedulers essentially stateless. And it also means that the cluster and task state introspection that you want to do, like a dashboard or constructing metrics, like that doesn't affect scheduling throughput nearly as much as a global single scheduler process that has to be that has to like basically export metrics or provide a dashboard, yada yada. So that's really nice. And then Apache Plasma, the distributed in-memory object store, which is used for peer-to-peer data communication and zero-copy intra-node reads, provides very, very fast local data sharing between tasks. Tasks are on the same node, and it's dealing with like ndarrays or really anything that's supported by like Apache Arrow. It will provide zero-copy reads, which is cool. And then there's support for fault-tolerant stateful actors. It's really the support for actors in Ray is truly first class. There's been recent efforts in Dask, but Ray, it was kind of like almost like actor first. Yeah, great support for stateful execution. And its scheduler is still really smart despite being decentralized. It's resource aware, it's local first. There's the scheduled decision caching maps a lot of scheduling decisions to essentially just worker-to-worker RPCs. It doesn't even have to consult the Raylet, or it doesn't have to ask the Raylet to please make a scheduling decision. And that, where as long as the task has the same resource shape and there's already a work release, then it's just a worker-to-worker RPC and it's super fast. And there's stuff coming down the pike such as locality-aware scheduling and work stealing. That's also super cool and very hard to do in a decentralized scheduler. So how do we actually get Dask to run on Ray? Let's try it out. Well, given that Ray tasks are just like, pickled Python functions, and given that Dask task graphs are just function application graphs containing Python functions in memory, and then, when decentralized or when the tasks are distributed, those Python functions are pickled. If we just convert each Dask task's Python function to a ray.remote function, like if we just Rayify it, we can execute any Dask graph on Ray. Very simple. So the Dask-on Ray scheduler is essentially this with some optimizations and extensions. We tweak the semantics of the existing local Dask scheduler, which already traverses the Dask graph and executes the tasks, to instead traverse the Dask graph and farm the actual task execution out to Ray. And then after all of the Dask tasks have been submitted to the Ray cluster as a Ray task, we just call ray.get on the output object reference on the sync node of the Dask graph, and that will then cause execution to wait and fetch the output of that Dask computation once that final output node has materialized. And so usage, it's very simple. It's like suppose some computable is like a Dask array or something, some sort of like a Dask object. Typically call compute. Instead, it turns into this. You just like connect to the cluster at one point in your program, and then you pass in the Ray Dask scheduler, the Ray Dask get. So really big kudos to Dask for making the scheduler so pluggable. It was very, very easy to create this. I think the initial version was like 8 lines. So yeah, we have, in addition to the scheduler, we've implemented these scheduler callback abstractions, which allow you to hook into the Ray task lifecycle. And this is something that people who've used Dask might be familiar with, the custom callback abstraction. This is pretty much the same thing, except it's Ray-specific hooks. And this makes implementing Dask level stuff like task introspection, such as like progress reporting, diagnostics, caching, super simple. We've used this extensively. And then we have a series of callback hooks. There's a pre-submit, which runs before submitting array task, post-submit runs after submitting array task, pre-task, which runs before executing a Dask task, and then post-task, which runs after executing a Dask task, post-submit all, that runs after all array tasks have been submitted, and then finally finish. After all array tasks have finished, that will run. And the pre-task and post-task will run within the Ray worker, like within the Ray task function, essentially. So time for some benchmarks. How fast is this? I thought it would be way slower in every case because it's super naive what we're doing. So we use a popular data frame group by benchmark, and where you you take a data frame and you do a group by and a mean. I've seen some Matt Rocklin blog posts before. Matt Rocklin, the creator of Dask, detailing this benchmark. He's used it before. So we write anywhere from 1 megabyte to 1 gigabyte of data frames to disk if running the benchmark on a single node, or to Google Cloud Storage if running the benchmark on multiple nodes like on a cluster. And we write those as Parquet files. And then the benchmark just reads those files into data frames and computes a group by and a mean. So very, very simple benchmark. So the single node case, we run it on a 96 core, 386 gigabyte RAM instance on AWS, a huge machine, just for fun. And very surprisingly, Dask-on Ray is anywhere from 10 times faster or anywhere from 2 times faster to 10 times faster on this single large machine, which was pretty surprising. I'm thinking possibly due to intra-node zero copy reads by the plasma shared memory. That's potentially an advantage for the single node use case. We tried to take pretty good care to make sure that nothing like the buffer cache wasn't getting hit by Dask-on Ray and not Dask and stuff like that. Like we are generating, for each case, generating completely random data frames and writing them to disk or GCS. So, but yeah, I got a profile more to find out why. It's really interesting. Now the 5-node cluster. This is each one has 16 cores, 64 gigabytes of RAM. This is on GCP actually. It's all these instances are N2 standard 16 instances. If you're familiar with those, this Dask-on Ray is about as fast as Dask Distributed, which makes sense because Dask Distributed's global scheduler is really smart. It has locality-aware scheduling. It has work stealing. It potentially might have some less overhead for the small cluster use case. Again, I gotta profile more. I'm looking forward to digging into this over the next couple of weeks. But there's lots of low-hanging fruit for Ray here because Ray does not have locality-aware scheduling or work stealing yet. So lots of potential fun stuff to do there. So what does Descartes Labs use Dask and Ray for? It's for our workflows product, which is a computation engine for interactive and batch geospatial data analysis. So here you see like this, somebody composing a geospatial workflow, a little geospatial model. They're composing a composite, and then they're visualizing on the map. And I'm not going to demo this today, but the map widget today. But when you pan around, it basically like recomputes on the fly. And then that's the interactive version. And then we also have a batch system. So the idea is you express your geospatial model using these high-level abstractions like image collection, feature collection. And then you express operations, high-level operations on these abstractions, and then you visualize the results on the fly. The workflow's backend will take an intermediate representation of those high-level operations, compile it into a low-level task graph, which will then do some automatic data partitioning to provide data parallelism in addition to task parallelism, and then it'll execute those tasks on a cluster of workers. And it allows for these high-level model descriptions that are pretty much parallelism and data partition agnostic. You could almost say like scale agnostic. And they can be transparently run over tens of thousands of cores, and then searching over and pulling petabytes of imagery from our data catalog. Programming model, very simple, kind of went over it a little bit already. We have these proxy objects in the client that the user imperatively manipulates, and under the hood, this composes a DAG of data transformations. which is represented in our graphed intermediate representation. And this gives us that lazy execution, which if you're familiar with like machine learning frameworks, or if you've used Haskell, you're probably pretty familiar with like lazy evaluation. And what's nice is this graphed IR composition is totally done on the client. There's no network communication or any interpretation of the graph until you call compute. Then once you call compute, it's sent to our backend and executed. So quick workflows demo. This is a fun one. So if you're not familiar with synthetic aperture radar imagery, this is it's pretty cool. It's a satellite that has like a radio antenna, and it emits pulses of microwave radiation and measures the echoes from the Earth. And there's a synthetic aperture that's created by the motion of the sensor in the orbit, because it's sending multiple pulses down to the Earth, measuring the echo. A virtual aperture is created by the motion of the sensor, which is pretty cool. It allows you to get super high spatial resolution imaging with a small antenna. And since it's microwave radiation, it's an all-weather day and night imaging system. Like it provides its own radiation, so you don't have to wait for the sun. And then microwave radiation does a very good job of penetrating clouds and all that jazz. We construct this like Sentinel-1 image collection. We're going to do a 5-year max composite. So there's that date range. We're going to pick the dual polarization band. I won't go into that due to a shortness in time. And we're only going to use the ascending orbit. So that's the orbit of the satellite that goes towards the North Pole. And then, yeah, we're going to do a max over the image axis, or you could think of this as the time axis as well. And then we're going to scale the values to 0 and 1. Now, one fun place to look would be the Strait of Gibraltar, that's where this geometry is. And we're doing a resolution of 200 meters per pixel. So this right now just launched the job over this AOI. Right now it's preparing, it's interpreting the graph, it's creating the Dask graph. And then when it's running, this is the number of Dask tasks. It's running, it's doing all of these computations, it's creating the composite, it's doing, the filtering. Cool, 18.5 seconds. It's about 30% faster than I've seen with the non-Ray backend, so that's pretty cool. And then now we're going to visualize it. And this might actually take a second. It might take almost as long as it took to compute the result, because I matplotlib. And so this is going to show us vessel traffic in the Strait of Gibraltar using synthetic aperture radar using a max composite over 5 years. So we get like a nice, cool, like peak summary of vessel traffic. Super cool. How cool is that? So you see here, this is the Strait of Gibraltar, and these are the shipping lanes. And even here, like Gibraltar, I'm sure like the Rock of Gibraltar is like right here. So this is Gibraltar, which is, I believe, like a British territory. And then you have Morocco, Northern Africa right here. I think, southern Spain up here. And then here you see this all should be water. So this is all like actually like clusters of ships. Super busy port. And if anybody wants to see, I've also had a lot of fun generating these images. So I've generated some offline as well. So these were 4-year composites, and it's nuts. Look at all those ships. So cool. And just to see like the number of images that we just computed that composite over, it's over 1,700 Sentinel-2 images, which is a lot of imagery. That's a lot of bytes that we just processed. And the fact that we did that in under 20 seconds is pretty cool. So yeah, that's a quick demo of workflows. So back to the presentation. And how about some benchmarks between the Dask-on Ray backend versus the pure local Dask backend? So one example here is a 3.5-year Sentinel-2 mean NDVI composite. NDVI is a very popular vegetation index. That vegetation, it's basically like I think it's like a 1 or 2 week proxy for vegetation health, the brightness of NDVI. And here we go. This is actually very surprising to me. Dask-on Ray is anywhere from 20%, 30%, uh, and then over, over 50% faster than plain Dask, which is very surprising. But still very surprising to me. I actually thought that it was going to be a good bit slower because there's so much overhead. We're creating the Dask graph, traversing the Dask graph to farm the tasks out to a Ray cluster, and yet somehow it's faster for these like medium-sized work use cases, which is surprising to me. And then the previously impossible is now enabled. For example, very temporally dense, lots of scenes, thousands upon thousands of scenes in this composite at a high resolution. The plain Dask backend failed with an out-of-memory error. And the Ray backend, I mean, it took a while. It took like over 3 minutes, but it did it. This wasn't previously possible with our last backend, which is cool. So future directions for Dask-on Ray. Where do we go from here? An actor native callback abstraction I think would be very compelling. This would be a tighter integration with actors when hooking into the Ray specific, like the Ray task execution lifecycle. And the reason why this is nice is everything that you want to do that does any sort of like aggregation of state is fundamentally going to require an actor. That's where you're going to have to do. And the current pattern is you create like a Ray Dask callback, and then you pass it an actor handle on instantiation. And then whenever in any of those callback hooks, in any of those methods that you implement, and if you need to do any sort of like state aggregation, you pass that state to the actor via like a remote method invocation on the actor handle. But we could have a much tighter integration. I didn't go that route the first time because there's some callbacks that don't need an actor, and then that's unnecessary overhead if you're having to do actor RPCs for pretty much everything. Move the unpacking and repacking of object references into core array. Right now in the Dask-on Ray scheduler, what you have to do is given that Ray does not traverse arbitrarily nested Python data structures to pull out object references and to loop them into the task's argument dependencies, you actually have to do that unpacking and repacking before task submission, and then flatten out the object references, and then pass a repackaging function and closure into the Ray task, and then within the Ray task do the unpacking. Do the repacking within the Ray task. And, I implemented that, it was fine, but it's something that could certainly be supported natively within Ray, probably more efficiently, just with like a little traverse keyword argument for like the remote function. A plasma-based caching solution would be great. Dask tasks are deterministic and pure in general, and they have like a content-based like hash within its Dask key. And we've implemented caching solutions on top of it before. But with Apache Plasma being a distributed in-memory, object store, it's like, well, the data's already there. It'd be great if like we could just if we could use Apache Plasma as the distributed cache for the Dask-on Ray system. And we've implemented that. We've had to jump through some hoops because of the object ownership semantics and not being able to transfer the ownership of an object to like a long-lived caching actor. Adding locality-aware scheduling in core array would bring us closer to the scheduling intelligence of Dask Distributed's global scheduler. And I think I've seen it mentioned a few times. There's some blockers, but that's going to probably be coming up in the medium term. And then work stealing, there's actually an open PR for that right now in Ray, which would be super, super cool. So that was my talk. Thank you. I hope that there are some questions. Thank you very much for listening. Let me know if you have any questions. Thanks.